last lecture. I'm going to do chapter 15, and then no new material next week. I'm just going to be here to answer any questions in case anybody needs anything. If you're turning in projects and discussions and quizzes and all that, try to get them all done by 5:13. Then you got a week to do the final. And if people are still turning in other things at this time, it's best to let me know to expect that and look for it, because I might not detect other things coming in at that time. Anyway, let's take a look at this last chapter. I must say we finished the whole book, which is good. I wasn't sure I'd do it this semester, and I find this very interesting. You know, I never really got a degree in computer science. I never learned some of this stuff. I learned a whole lot of it in industry, working with all computer systems and stuff, but I never really understood how GPUs work, and now I understand them better. So, that's the game here. So, we're going to talk about hardware acceleration, CUDA, distributed memory systems, and some stuff beyond that. So here's the type of architecture. You can either have a single stream of data or multiple streams of data being processed at the same time, and you can either have a single stream of instructions or multiple streams of instructions going on at the same time. So you got single instruction, single data, all the way up to multiple instruction, multiple data. And so this is a single control unit. This is the kind of machines we had in the 90s. One processor with one core, and it can only do one thing at a time. This is basically MS-DOS and such. All right, and then multiple instructions, single data. This doesn't happen very much. Single instruction, multiple data, that's what GPUs are. GPUs have multiple data streams, but they're all executing exactly the same code in lockstep, step by step. But MIMD is modern multi-core GPUs that we've been talking about before, where you have multiple cores and they each have their own memory stack, and so they can each be running different code and each be processing different data all at the same time. And so you have to have those mutexes and those other techniques to try to avoid them undoing each other's work. All right, so hardware acceleration. Here, heterogeneous computing is going to go here, various ways to do it. Heterogeneous computing is where you have multiple different processing units. And this is the way a lot of modern computers are, including the one I'm using right now. It's got a CPU with two kinds of cores, efficiency cores and high performance cores. And then I think it has a GPU or a TPU, or both. It's the Mac M4. I think it actually has a TPU. So it has two kinds of cores in the processor, and then it has a tensor processing unit too. So it's got several different kinds of processors in the same machine, and they often have different instruction set architectures. So that means you do have parallel computing using the cores. So you got the CPU cores, and you have something else like GPUs or FPGAs, or in my case TPUs, tensor processing units. And I don't really know exactly what tensor processing units are, but they're considered more useful for AI than GPUs, and otherwise similar to GPUs. So, you know, we're going to go to GPUs in some depth here, but I haven't read a similar in-depth analysis of exactly what TPUs are. I just hear about them as considered to be the even better thing to use for AI. So FPGAs are reprogrammable devices. So you can program it to be like a hardware processor with certain built-in code in the processor. So they're relatively expensive and hard to program, but you can now set up ASICs. And ASICs are when you make a special chip just to do one job. One case I know about this is Bitcoin mining. When Bitcoin started around 2010, you could just mine it on a normal computer. But mining is a competition. Every 10 minutes, all the miners run, and whoever has done more calculation is more likely to win the prize for that 10 minutes. So the fastest machines set the standard, and the slower machines are pretty much just wasting their time. So as the years went by and the price went up, people kept getting more and more expensive Bitcoin miners. So they passed the 10 when normal CPUs could do it several years ago, and then everybody switched to ASICs, which are special chips made just for this one purpose, and that is the fastest way to do anything. Get a special processor that just does this one job. And in FPGAs, you can prototype an ASIC. You can make it's programmable, but once you program it, it runs with that program built into the chip, so it runs very fast. So this is often what you do to make test new hardware designs, which you may eventually make special chips just for that purpose, ASICs. So cell processors are a multi-core processor with one general purpose processor and multiple co-processors, and the Sony PlayStation 3 worked this way. And I remember about, no, and a good question, are ASICs repurposable? No. The ASIC is hardware designed to do one job, and that's it. It's only going to do that one job. So if you have a Bitcoin miner, that's all it can do is mine Bitcoin. You can't repurpose it to do something else. That's why it's extremely efficient at that one task, because it's not general purpose. It does not have any extra chips in there for any other job. It just has the chips needed to do this one job as fast as possible. That's the idea. Now, the FPGA can be repurposed. It can be reprogrammed, but it does give you a prototype of the ASIC. That's a very good question. So the PlayStation 3 was a cell architecture, and about 10 years ago, this was the common way for people to make a supercomputer. And the hackers that made the first forged HTTPS certificate in, I think, around 2012, they actually managed to compute enough hashes to forge an MD5 signed certificate and make a forged HTTPS certificate, which was supposed to be impossible, but it's not exactly impossible, it's just very difficult. And I think they did it with a cluster of a whole bunch of PlayStation 3s. You could buy like 10 or 100 or 1,000 of these things for relatively cheap and have a cheap supercomputer because of this at the time. Now the GPUs are what gives us this power, and almost everybody has these. The original purpose, of course, was to play games, primarily on Windows machines, but they turned out to be so powerful that you can use them for a whole lot of computing activities. So this performs computer graphics, and we'll see how it goes. So here's the GPU, here's how it looks. You have streaming multiprocessors here, which consist of a whole bunch of scalar processors. So these are the processors, and what happens is you have a warp scheduler, which will take a set of threads and put them on all these little processors, and you have a lot of them. You have these streaming multiprocessors that includes a whole bunch of scalar processors, and then you have a whole bunch of those streaming multiprocessors together. So you might have 512 computing cores or 1,000 or 5,000 on your chip. And they all run exactly the same assembly language instructions in lockstep, all at the same time. So this is multiple streams of data, but only one stream of instructions. The warp, which is a set of threads, are all just executing the same instruction one after another. So that's why it's intended for something like graphics, for you doing something like adjusting the contrast of an image or rotating something in 3D. So it's doing exactly the same code on every little pixel, moving it around. But you can apply it to any other job that can be broken up into this many independent little chunks, like password cracking. You could take all the possible passwords and put a certain set of them available for each of these and do the identical calculations on each one of these, processing on different data. So GPU computing is general purpose GPU computing, and that will take these special purpose GPU processors and perform general purpose parallel computing tasks. Now these are not ASICs, the GPUs, they're running code, and you can send them any code you want. So they're not hardwired for just one task. That's the good thing, but they are massively parallel. So if you have some task that could be broken up into 5,000 parallel streams, then it will be much faster to do it on a GPU, of course, than doing it on a CPU that's only going to have, like 4 cores or 8 cores or something like that. So the host operating system does not manage the GPU, processor, or memory. What you do is you just copy the memory into the GPU memory and copy the code into there and then set it off. It's a coprocessor. So you feed it the data and instructions and then you let it go, and then it gives you the answer. So CUDA is the programming interface for NVIDIA, which is the main manufacturer, the highest, the one making the most money, the standard. And so CUDA kernel functions run on the GPU, and they're marked global, and a CUDA thread is the basic unit of execution of a CUDA program, and like I say, they're in warps, which is a group of threads, all running on different cores in the GPU. So you'll allocate some memory with CUDA malloc, which is not allocating it on the heap, it's allocating it in the GPU. This will create some GPU memory, this will free that memory, and here's the memcopy program that will copy data from source to destination. So you prepare the data on the CPU, you copy it into the GPU, then you set it off, the GPU runs, and you copy the data back. So the threads are organized in blocks, and the blocks are organized into a grid, and you can treat these as an array in 1, 2, or 3 dimensions, and that's obviously because the primary purpose this was all intended for is to do computer graphics, where you might have a 2-dimensional image, or you might have a 3-dimensional object which is being projected down to 2 dimensions, and so to make it easy to organize these thousands of threads and cores, you can organize them in a pattern that will logically match your problem. So here's how you specify the dimensions: 256 threads per block in a 16 by 16 2D arrangement, and here's 400 blocks per grid in a 20 by 20 arrangement. This can be 1, 2, or 3 dimensions at these levels, but you design it to number them in a way that's easiest for you to understand in your application. And then you'll call a kernel function, which is here. Going to pass in those dimensions, and then you're going to pass in whatever parameters are needed. So you have threads here, and the threads are in a block, and the block is in a grid. All right. So here's an example. If I want to do scalar multiply, where I'm just going to have a vector with 5,000 elements or something, and I'll just multiply each one by a constant, then you allocate host side memory for the vector and initialize it, then allocate device side on the GPU for it, and copy it from the host to GPU memory. Then you invoke a CUDA kernel function to perform the scalar multiply. You pass up the instructions you want it to go, pass them in with arguments, and then you let it run, and then you copy the result from GPU memory back to the host memory. So it's a pretty simple process, the way you'd use a second processor for anything. And so here's what it looks like. You allocate host memory space with malloc on the heap. Then you initialize the host memory array. Then you allocate GPU memory with CUDA malloc. Give enough room for your vector. Then you copy the vector from the host to the GPU. Then you call the CUDA scalar multiply kernel, which is here. And you copy the device vector to the host memory because it's done now. And then you free the memory on the GPU and on the host. That's the whole story. All right. Now, what I don't know is exactly how you wait until it's done. I'm guessing this thing must block until the task is done, so I'm not quite sure about the timing here. But anyway, that's generally how it goes. And so here you compute the calling threads, index value, and this is the scalar multiply function that was passed to the GPU, and this is written to be run in a multi-threaded way. So it's going to have a index here, and the index, it's going to calculate which thread it is. So it's going to take the block and the block dimension and the thread ID and figure out which thread it is, and then it'll calculate what part of the array it should work on. So that the 2 threads don't work on the same part of the array. It'll get the index number, which is which thread I am, and use that to figure out what part of data I should be using. All right, which we've done before in other cases. All right, so all the threads in the work execute the same instructions in lockstep. CUDA guarantees that all the threads complete before any threads from a subsequent kernel call are scheduled. So it's a very simple process. All the processors must be doing the same thing until they're done. And then they get another job and they do that till they're done. So like I say, not all that general purpose. It's only going to work for certain kinds of problems that can really be broken into this many identical chunks. But it turns out there's a lot of things that can be broken up like that. And those things are now thousands of times faster because of these GPUs. And you can use other languages for some of them, like OpenCL, OpenAC, and OpenHMPP. These are the non-NVIDIA languages available. So OpenCL is one that targets a wide range of devices, including CPUs or FPGAs. And OpenAC is a higher level abstraction program, which is probably easier to write your code in. And then OpenHMPP is another language at a higher level. So these are alternatives. But the one I hear about most, of course, is CUDA and NVIDIA. That's the standard. Most people are writing code for that. When I read machine learning models and stuff, they all say, you have to have NVIDIA, you're running CUDA, don't waste your time on anything else, But that's changing as there are more and more of these fast processing coming out. But that's the standard. That was the earliest one in the standard. So let's take a look at Kahoot, which is here. right, there's the number. Let's see if it stays visible. Looks like it does. Good. All right. Good. That's free points for if there are only 3 players, they're all going to win. Anyway. Oh, good. Yeah, give it a little more time, see if we can get any more players. Oh, good, good. All right, let's give it a shot. All right, so which type of processor is a GPU? A single instruction, multiple data. All the cores are doing the same thing in lockstep, but they have independent, different data for each core. All right. All right, which system combines different kinds of processors? Yep, that's heterogeneous. That's what it means. You have different kinds of processors working together. All right, and which function is called last in a CUDA program? All right, CUDA free, you kind of logically, you allocate some memory, you copy some data to it, you run the program, and then you free it. So free would be the logical end of your code. All right. Whoa, I programmed this one, okay. All right, good. All right, let's get back to here. So, distributed memory. This is a set of computers working together, so supercomputers can do this, and COTS clusters, commodity off-the-shelf clusters. So a supercomputer has many computing nodes tied to a fast interconnection network, and these are usually racks and racks of computers in a room with special cables and special networks like fiber channel or Ethernet connecting them all together, and probably to a bank of storage devices and such. I've seen these at Lawrence Livermore Lab, and they're really quite impressive. Whole room full of computers to do things like model nuclear explosions and predict the weather and things like that. And a COTS cluster is a shared nothing architecture, and here you just have a bunch of completely separate computers connected by a network. So each computer has its own cores, its own main memory, its own I/O and everything. Nothing is shared at all. It's only connecting over a network, which might even be over distance. And so these are completely independent machines that are then working together to do something. All right. All right, so then there are various ways to make these distributed processing models. A client server is the way web servers work. This is a very common model. You have one server at some kind of fixed address, and many clients connect to the server, and they request something from the server, and the server hands out whatever you got. Typically, like you're a web server, you have files. They ask to see a page, you send them a copy of the page, each one by one. So the server process waits at a well-known address and responds to requests. And of course, if the central server goes down, the whole thing is over. The clients can't get anything done. So that's the client server model. Now, a pipeline divides an application into steps, each of which can run independently, and then they get run on different machines. So, for example, if you have a computer animated film where every frame has to have certain adjustments done, and that's a whole lot of work, then each one of them can process independently. So your parallel processors can work independently on the different data elements. Boss worker is like client server. In fact, I'm not sure I really understand the difference, but the boss acts as a central coordinator. Oh, I understand. In a client server, the clients ask for something and they get it, but the clients are deciding what's going on. In the boss worker, the boss is deciding what's going on, so the boss will assign the client some work and then collect it. And this, I think, is, for example, folding at home. I don't know if they're still doing folding at home because I think AI replaced it. But for a few years ago, they had you could join a thing. If you had a Windows machine, you could run a screensaver that would use your machine's CPU when it was not busy to calculate protein folding. And so the central server would send your machine a certain amount of parameter space to explore. And your machine would explore that and then send the data back to the central server, and it would send you another batch. And that's the boss worker, where it just assigns you some work and then assigns you some more work and is splitting up this huge task into small chunks and assigning it to different workers. That's the kind of thing here. All right? And peer-to-peer, of course, is like BitTorrent, where there is no central device and therefore it doesn't have a single point of failure, where each one contributes to the overall network activity independently. So in BitTorrent, you take files like a movie you're trying to share. It gets broken up into many small chunks. Each chunk has a hash value, so you can tell if it's been delivered correctly. And when you want to download a movie, you connect to dozens or hundreds of peers and say, do you have any part of this movie? If you do, send me whatever chunks you have. And you gather all these chunks from all these different machines out there in a sort of random way, and then you verify that they're accurate by the hash value, and then you just piece it together, piece by piece. Does anybody have piece number 12? Does anybody have piece number 100? You build it up gradually. And if any of those machines go down, or any of the network connections go down, it doesn't really matter. You just go find other peers. There's no central machine, no way to stop it. And this is the way Bitcoin works, and this is the way BitTorrent works. And both of them are intended to be impossible for anybody to take down. No government can take it down. No law enforcement agency can really take it down, because even if you turn off a bunch of servers, the other servers will keep running. Even if you somehow ended it in an entire nation, the other nations would still be able to access the network. It isn't over until all the peers have stopped running it. So as long as there's anybody on Earth that wants to run it, then it will keep going. That's the idea. All right. So you got communication protocols. You do message passing, where one process sends a message to other processes. Of course, you do need to have some kind of communication for these guys to coordinate. So some applications require frequent coordination. Others just divided among processes, like that boss worker thing, where it just sends you a package of work and says, you don't have to talk to me until you're done. Then send the results to me. That's one way, but other things require closer coordination. So you got a communication protocol, which specifies when you send a message, how to format it, where it's going. Without a protocol, if you don't have an organized way to send messages, then you might have a deadlock where two processes are waiting for each other to send a message and you stop dead. Like we talked about, this can happen before with threads. So that's why you want to have a properly organized protocol to make sure that doesn't happen. Because remember, the problem is you have a bunch of programs running on different machines, and those machines might go down. They might have a network loss of connectivity. One might run slower than another. So you can't make an assumption about which one is going to finish first, or this one will be done in time for that one. You have to make it tolerant of failures and delays all through the network. This is a big deal. And I know at Netflix, they were proud of the fact that they told everybody to program for failure, and then they added a chaos monkey agent to the system. So at Netflix, the Chaos Monkey randomly turns off servers and network connections all the time so that everybody has to stay disciplined. And they say, whatever you code, you have to code it so it can withstand a failure of some of the network connections and some of the servers. And we're deliberately making them just randomly turn off all the time just to keep everybody, on their toes about that. And they say that's very successful. That's why their services tend to stay up, because everything is written in a robust way. Anyway, so the MPI standard is one way to do it, and that makes your applications portable so they can run on different systems. And so you divide your application into multiple processes that has a rank number, and they run all over the place. So here's the main functions. You can find your rank number with this function. You can find out how many processes are executing, send a message, and receive a message. And you can broadcast. If for example, if you were doing password cracking, you'd take a huge list of like millions of passwords and you give every machine like 10,000 of them to try, and they'd all be calculating hash, seeing if it matches a certain value. And then if one of them finds the password, it would probably like to send a broadcast to everybody. Okay, stop. We're done. I found the answer. Nobody else needs to keep working. That might be a case where you might want to broadcast. And scatter will divide an array and send the pieces to all the processes, and gather will retrieve all the data. So, here's Hello World. In MPI, you import the MPI library, and then you initialize MPI with MPI init. Then you determine how many processes there are and which one this is, because this is a multiple threaded, so all the programs are running the same code. So you determine the number of processes and which particular one I am. Then you get the host name of this machine, and then you just, in this case, just does Hello World. Hello from this process on this machine. So that's Hello World. And so when you run it, you'll get, and then what they did was they made two computers, one named Lemon and one named Orange, and each one of them is running, I think, 4 processes on it. So a total of 8 processes. So here you get them, and they all come in a random order. The processes are labeled 0 through 7 of 8, and some of them are running on Lemon and some of them are running on Orange. That's what you get. All right. So if you want to do scalar multiplication on an array to be a little bit more interesting than the Hello World, then you have, you're going to need to do boss worker. So we're going to have this stuff. If rank equals 0, then you know you're the boss. So that's how you're going to write code that can the boss will do something different than the workers. And so the boss will send the scalar value and the size of the array to the workers, divides the initial array into pieces, and sends a piece to each worker. Each worker will do its part of the job and send the result back to the boss. So every process executes MPI broadcast, but what you do is if the rank matches the 4th argument, the caller is the sender. Otherwise, it sends it to everybody else. So each process determines how many processes there are. Then the boss sends the total array size here, and then you determine how many array elements each one will get, which is the total amount divided by the number of processes. And then you'll distribute the array. So if you're the boss, then you'll send a unique chunk of the array to each worker here. Otherwise, you will just work on the chunk you got. So that's how you do it. It's how this is because they're all running exactly the same code in a multi-threaded way. So this is how you tell the boss to separate from the workers. And it's just sending a chunk of the array. And then you aggregate the results. So if rank, this is the boss again, then for each process you receive the array and accumulate it. Otherwise, you just send it. So the non-bosses send it to the boss, array number 0, and the boss accumulates them all. And if you use scatter and gather, it becomes much easier. You just use scatter to split it up and send it to everybody, and then gather to bring it in. This is the higher level code where it's much easier for the programmer, where the details are all automatic. So that's pretty fun. All right. And so that's distributed system challenges. And like I say, you have to consider what can go wrong. Every node can fail, every network connection can fail, things can be slow and so on. So you have to be considering what to do if that happens. And the nodes don't share a clock. You're not synchronized in any way probably, so you don't really know when they're done. Another application I know that runs this way is Velociraptor. Velociraptor is something I use a lot for incident response. You have a central server, and you might have 10,000 computers scattered across the world, and you want to send a query to all those computers. Like, so you're getting an infection spreading through your network, so you determine the machines that are infected will have this registry key and this file being created. So my question for every machine is, do you have this registry key and that file on you? So I send out a request, and it's designed to be asynchronous. It sends out an asynchronous request to every machine, like email. Each machine will then run an agent to see the answer and send it back, and it's all independent. Nobody is waiting for anything, which is important because some of the machines might be down, some of them might be powered off, some of them might be disconnected from the network right now, so you don't want to wait for all the answers. You send out the query, which goes out, then each machine runs. There's a time limit for how long each one of them can run before it gives up, like 2 minutes, and then answers come in gradually, and you see the results on the server. This is the way you have to think to plan a distributed task like this so that it doesn't end up hanging up and crashing or burdening anybody too much. You have to think about all this, make sure that the server isn't waiting for something that might never happen, make sure that none of the clients are being caused to fail by what you're asking them to do, because various things might be wrong with the client, especially since they might be infected. So, you have to think about these things. All right, and so exascale and beyond, this is high-performance computing. You write your application in a high-level language with multi-threading and message passing, and you use one of these libraries, and then you can have high-end data analysis systems, which process a deluge of data, and this is what people do if you have just a huge amount of data, like Facebook or Google, where you have all these people sending queries to the search engine at the same time, all these people sending posts to their Facebook wall, and you have to have a huge cluster of servers all handling that huge deluge of data, parceling up all the work and spreading out among all the servers. So here's the HDA uses data centers. So you have machines running all different operating systems, virtual machines or containers, networked together, and you're using things like Spark and MapReduce here, which we'll talk about more, to provide these cloud services we're using, like Gmail and such. The other one is high-performance computing, where it's always Linux, and it's all designed to work together, and you're using languages like CUDA and such for scientific instruments. This is like what they have at Lawrence Livermore, a special device built just for this purpose, high-performance computing. Here you're tying together a lot of machines that might be all different. So cloud computing, there's 3 ways to do it: software as a service, infrastructure as a service, and platform as a service. And the only difference is how much the end user is in control of the system. So software as a service is by far the most common, like Gmail, where the developers have written the code and you can't see the code or change it. They've installed some operating system. They're handling updating versions, updating libraries, whatever. All you can do is use the program. They give you some buttons to click: send your mail, receive your mail, put a star on this message, and all you can do is the functions they give you. That's it. You're just using software somebody else has written and maintaining. You can't get a shell on the system. You don't control the operating system. You can't add more code to it, except if they give you some kind of limited, coding functionality. That's software as a service. And this is, of course, extremely popular. Everybody uses this all the time. Infrastructure as a service is the next step towards having more control. You rent a virtual machine, like Amazon Elastic Compute Cloud, and now you have to install your own applications and data, and perhaps even the OS yourself. You're just renting a cloud server, and the main thing you're getting here is you don't have to maintain the hardware and the backups and the power and the cooling and all that. You're just renting a virtual machine on somebody else's iron. And of course, I do this a lot. This is how I run cloud virtual machines for my students to hack into. They're specifically running vulnerable old versions of things. But anyway, normally you don't want this. Normally you don't want the responsibility of having to install the operating system and maintain the updates and everything. Usually it's enough to let somebody else take care of that if you want a standard job like a web server or something. But if you need custom work, then you probably want to do this: rent a virtual machine in the cloud. And the most extreme, where you get total control, of course, if you're still in the cloud, is a platform as a service, where you deploy your own applications inside the engine here. And this is where you make a web application, and I've also heard this called serverless computing. You put up an application, and they distributed across many servers. So you can do this like Google App Engine and so on. Cloudflare also has a version to do this, that your application lives in the cloud, it gets requests and it responds, but it's running on servers that they, at their choice, and moving from one server to another as they decide to redistribute the load, and you don't really know or care which server is running it. That's another way to do it. Anyway, all right, so MapReduce is a technique to make it easy to program this sort of thing. So the map operation will apply a function to all the elements, and reduce will reduce the elements. And so in Python, you can see something like this. If you do something with a for loop, you have a range and you do a calculation on every element of the array one by one. This is the old-fashioned Fortran way, which is what I'm used to. But the modern way is list comprehension. You include the for inside here. And it's just a different way to write it, but it is letting Python itself make the loop and split it up into chunks. So here's the MapReduce model. The map function you write, it takes an input of keys and values and creates intermediate key values written to a distributed file system. Then there's a combiner which aggregates it to produce key and list. It makes a list of the values for each key value, and then reduce combines all the values. That's the map and reduce. That's the idea. And this is a word frequency program. We talked about this, or we had this one here will take a bunch of language and it will break it into words and then count how often each word occurs. We haven't done exactly this task before. We've done similar ones. So here you have you define some initial variables, and now we're going to find the words. It's going to parse this input data to find the words, and then we're just going to go through it one by one and break the words up. This is going to make a list of the words with a number 1 for each word. So it's just going to take each word and put a 1 into it. That's the initial data coming in. So this is the map part that just takes your data and prepares it for processing. Then the processor runs, the operating system takes care of that, and then you have the reduce when you're done, where you just go through it and bring the add up all the counts for each word, and emit the answer here. So you output your key and string totals for each number of words. Right, so you're going through the whole list. I think I'd have to go through the list twice. That's why I'm a little confused here. Total is yeah, I don't quite understand what this A to I thing is doing. But anyway, this is what's combining the subcounts into a total count. It's easier to see in the picture. So here's the input file, which is this little poem. And so the map part just takes each word and puts a 1 next to it, and it doesn't worry about the fact that you have monkey here and monkey there. Then the aggregate combines them, so it takes all the monkeys and makes a list of all the numbers that go with them. So it just aggregates them, and then the reduce adds these back together. So you only code the map part and the reduce part, and the program in the middle does this aggregating part. That's the idea. So the point of this is to be fault tolerant. There's one boss node and possibly thousands of workers. Therefore, it's likely that some of the workers will fail. So what it does is it checks with the workers to see if they're still up and running. And if it doesn't receive a response, then it reassigns that work to another node, just like any kind of boss would in any kind of company. And that's how it goes until all the work has been done. This is very much like BitTorrent, where it will try to fetch every chunk of the file, and if it doesn't get it, it will ask somebody else, do you have that chunk, until it finds it. So Hadoop. Now, Google's implementation of MapReduce is closed source. So Yahoo developed Hadoop, which is the open source implementation of this. And that was later adopted by Apache and became Apache Spark. So Hadoop has Hadoop Distributed File System and HBase, the components of it. And Hadoop had limitations, turned out to have bottlenecks and limitations, so they developed Apache Spark to be the improvement of Hadoop. And it turns out to be much faster than Hadoop on certain applications. So that's the game. And all right, so in the future, we got centralized computing. There's a lot of argument about doing things at the edge and doing things at the center. This is now that we have very powerful home machines and also powerful servers, it would make sense to spread jobs, where some of it's done at the edge of the network and some of it's done in the center. So people worry about this. So they gather data, analyze it using a local cluster, or move it to a supercomputer. This is the centralized computing, and people are trying to move to edge computing. And this also includes Internet of Things devices. There's all these different models for different tasks. Some of it's done on the server, some of it's done on the edge. And then, of course, there's the issue of big data and data lakes and so on. There are a bunch of people that are working with monstrously huge databases, especially in machine learning. In fact, I've read articles that claim that machine learning models, large language models, have probably gotten as good as they will ever get already because they've simply run out of data. They're already training them on all the data on the internet, and there is no way to get a lot more human readable data. That's why Twitter and Facebook thought they would become leaders, because they each have access to a huge flood of newly written human data. But they both have serious problems in that on Twitter, a lot of that data is in fact from large language models, and even a small component of artificial data mixed in with the human data poisons it and makes it much less useful. And other problems too, like Elon Musk trains his XAI on Twitter, but Twitter is all full of disinformation and lies and Russian propaganda, so his AI is full of false stuff. So if you ask it medical information or political information, it will tell you false answers, which he likes because he's very much switched into this modern conspiracy theory world where he believes all these crazy conspiracy theories and thinks they're the truth. And so does XAI, so it puts you in this sort of science fiction fantasy land instead of the actual world of truth, which is what I think the Facebook model tries to do. Anyway, that's a problem. Anyway, but they've kind of run out of enough data to train these big models to get much better than they are. That's at least one analysis. All right, so they now have edge or fog computing. Like I say, instead of analyzing at the supercomputer, you analyze at the source of data production. So if each of the end devices does some pre-processing, then there's less for the server to do, and that's more efficient because you harness all those edge device computers to add to it. So you converge these things, and that's big data exascale computing. Looking at the cloud computing as a new way to take these data sources generated all over the internet and try to get the edge devices and the central devices working together to process all this data. So artificial intelligence, I mentioned, is a big one. Quantum computing is a really big one, but quantum computing hardware is still in development. The current quantum computing hardware is just very early prototypes, but they're coming. And so you've got new domain-specific architectures like the one I mentioned before, tensor processing units, which are the new, even more powerful replacement for GPUs for AI. And that's the game. And so we're going to have new languages, new operating systems, and new hardware as we move into more high-end parallel computing. Anyway, let's do the last Kahoot here, which is here. I got a friend who works in high-performance computing on supercomputers, but I've never done it. A new quantum computing breakthrough. Well, I don't know. Let me see. Looks like a joke, but I'm not sure. All right. It's a video. I'll look at it later. Looks like my thing is frozen up. Let me refresh it. All right. It's just my browser froze up. I've noticed that about Twitch. You have to refresh it now and then. The client freezes up. Aha! We may have a real competition here. I'll give it another few bars. All right. All right, so which architecture uses shared nothing? That's a COTS cluster, just commercial off-the-shelf machines connected together. That can all be different. All right. All right, which model is used to distribute web pages to browsers? All right, that's client server. That's what it is. You have one server, and the clients come and ask for service at their pleasure. All right. And which one is closed source? Yeah, MapReduce is the closed source one. All right, let me record the winners, and then I do know what to say about Majorana computing. Okay, 3 is a manual. And Laney and Lee. All right. All right, let me stop this recording.